Sonra ada. This is the second video of our physics video series, and in this video we're going to talk a little bit about units and measurement. Measurements is not only in physics, but it's important in every natural scientific branch. So first of all, let's begin with the question, what is a unit? Well, in physics, we are going to make a measurement, and we need a way to describe our measurement. In our measurement, we're going to have a quantity related to that measurement, and we talked about quantities in the last video. And to describe a quantity, we need a unit. Because saying only a number like 5, 6, or 10 gazillion something doesn't really make sense when you're talking about the actual reality. You need to somehow define these quantities. And anything can be considered a unit if it's defining this act of measurement. For example, you can say that you have 5 apples, and that measurement of apples would be considered a unit. Or we can go more scientific and say that I have 6 kilograms of weight. So that's fun and all, but how do we derive these units? So in physics, we're lucky because that our mathematical system is a coherent one. What does that mean? A coherent system. Well, it means that if you have just a handy amount of what are called basis units to describe the most basic measurements that you're doing, you can derive all of the other units that you're going to use from these simple ones. And that's exactly what we're doing in the entirety of classical physics or modern physics or in anything. The most used case are the SI units. Now, the SI unit it is an abbreviation for the International System, by the way, SI units. It has 7 basis units. It goes as time, length, mass, current, temperature, amount of substance, and luminous intensity, which is a measure of light. To ponder for a second here, these units are not mandatory. Okay, you can think of these units as a preference. You can think of them as a mathematical axiom. It's not always supposed to be these units that we're taking as basis units. Because, like I said, you can basically derive every other unit from these units. In the same way, if you're doing it correctly, you can derive these units from every other unit. That's why we have different unit systems for different purposes. For example, you have the base Planck units. This is usually used in quantum level stuff. You don't have to know this for TIL, but I'm just showcasing it so you have an idea of that anything can be defined in any way. You can define all of the other units as the Planck length, Planck mass, Planck time, Planck charge, and Planck temperature. Actually, it's not entirely correct when I said every other unit, but we don't really use the units that we can derive in this topic, so we don't need it. So the idea in units are that, like I said, we can derive every other unit from these basis units. So when we are dealing with units, we can deal with them in an algebraic notion. What do I mean by that? So since we have these 7 units, we can showcase all units like this. Let's say that we are trying to define the units of velocity, which you know as meters per second in SI units. You can also represent this as s to the power of -1 times m to the power of 1. Makes sense. And you can also add, we usually don't, but to showcase is that you can say that it's kilograms to the power of 0, amperes to the power of 0, Kelvin to the power of 0, moles to the power of 0, and candela to the power of 0. They don't matter, but I'm just writing these to showcase you that every unit can be represented in this way with just different numbers in these powers. So I'm telling you this because often in physics we're going to be dealing with units quite a lot. That's why I'm going to talk a little bit about dimensional analysis. Dimensional analysis is, well, dimension in physics. You can think of it as a different terminology for describing units, but you can think of units as these and the dimensions as these. See the correlation? Makes sense? Kind of? Yeah. The thing is, we can represent these dimensions with other symbols such as T for time, L for length, and M for mass. Most likely in TIL tests, we're going to be doing dimensional analysis on these 3 dimensions. Or maybe you can see electrical currents or other dimensions, but not likely. When doing dimensional analysis, we need to first consider what is the physical quantity that we're dealing with. Again, I'm going to give the example of, actually, you know what, let's give a different example for the sake of this. Let's say that we're trying to find the dimensions of the kinetic energy of a system. The kinetic energy of a system is described as half times the mass times the velocity squared. When doing dimensional analysis, what you should be considering also, let's note that the dimensions of a quantity is showcased in these brackets, these square brackets. When doing a dimensional analysis, you should first consider each of the dimensions of these single elements inside a whole quantity. This is mass, this is velocity, which is described as length divided by time. But since this is velocity squared, it's going to be length squared times t squared. Like I said, we can deal with this as if we were actually dealing with as an algebraic equation. We can write the dimensions of the equation the same way. And the dimensional analysis of our kinetic energy formula in the most simplest form would be this: m times L squared divided by T squared. Or if you want to describe it in another way, you can say that m to the power of 1 times L squared times T to the power of minus 2. When dealing with measurements, you're most likely going to encounter these prefixes. So these prefixes are basically describing how we want to write our quantity. For example, when you're describing the length of something, you can either say that it's 2,000 meters, or 2 times 10 to the power of 3 meters, or 2 kilometers. These prefixes are just defining the power of this base. And you need to be able to convert from one to another pretty quickly. You'll most likely not going to encounter these big prefixes like iota or zeta or exa. These are used in very big measurements like astronomical measurements. In daily physics and in TIL physics, you'll most likely encounter prefixes into these points. Anything under or on top of that is a pretty small possibility. Is significant figures, or also known as sig figs. When we're doing a measurement and we are trying to estimate a certain value, we are going to be using sig figs. Why? Because, well, if we're doing a measurement of big scale things, you're really not going to be able to measure every single tiny change. So you're going to estimate that value, approximate it to something close. And when you're estimating it, you need to be able to understand how many significant figures you're going to use in that estimation. But what defines which of the digits is a significant figure or not? There are a couple rules to that. So the first rule is that any non-zero number is a sig fig. So 536, all of these are sig figs, which means that this number contains 3 significant figures in itself. Any leading zero numbers are also sig figs, meaning that 0.0536 gives us a number of sig figs equal to 5, because now we have 2 leading zeros. If we have zeros after a non-zero number, like in 500, we only have 1 significant figure. Which makes sense because when we're estimating, and if your data changes by, for example, 3 digits, it's 503 now, you're still going to be estimating it to 500. So the only significant figure in this number is the 5. A tiny detail is that if you have this dot in here, then you have 3 significant figures. now you're counting the zeros after the non-zero number. And also, any zero between different non-zero numbers are also counted as a significant figure. And this gives us a 3 sig fig number. So that was the end of our video for units and measurement. Hope you like that.